So welcome back, everybody. And for this afternoon session, it's my pleasure to introduce Clément Delcamp from ICS and talking about entanglement and renormalization of spin system in the generalized Landau paradigm.
Thank you very much. Thank you for organizing this workshop and inviting me to speak. I'm actually not going to talk about most of what I wrote on this title, so I'm not going to really talk about entanglement. Renormalization will be only briefly mentioned, but I'm going to talk about spin systems. So that's that. And so I want to start with like a very simple question, at least simple to state a question, which is very physical question when you're dealing with a spin system, and that's usually maybe the first question you will ask if you're given a spin system, is to compute its ground states and how to efficiently compute the ground states of such a spin system. So I'm going to introduce some definitions so that this question is clear for everybody. We're all on the same page. But ultimately, I'm going to address one very specific aspect of that question, which is essentially how to answer the question, how to most efficiently compute such ground states. And in order to do that, I'm going to talk about something completely different. So I'm going to talk about topological field theories and the categories of boundary line operators of such topological field theories. But ultimately, this will allow us to answer this question. But so for now, let's stick to physics and to let me introduce the keywords in this sentence. Okay, so this is very loosely based on the work that appeared last year in collaboration with Lawrence Students and Frank Bachelor. So first of all, what is a spin system, or more specifically a spin chain, which is a spin system in one spatial dimension? So space is one-dimensional. There is one direction for time. It's a 1+1D model. It's a quantum mechanical model in the discrete. So it's built on the lattice. The degrees of freedom are localized around they are localized at a specific point of space. So the chain itself is going to be a subset of the one-dimensional lattice. The elements of this subset are referred to as the sites. This is where the local degrees of freedom are localized. And these degrees of freedom, they are essentially, they live in a d-dimensional complex Hilbert space that is associated with every site of this chain. The total Hilbert space is just the tensor product of all these local Hilbert spaces. And so a state, a vector in this Hilbert space is basically a quantum configuration for the degrees of freedom. Now, these degrees of freedom, they are acted upon by operators, local operators, which are just, so we have a matrix algebra of operators acting at every site. And the total algebra of operators is just, again, the tensor product over all the sites of this chain. So it's a C-star algebra. So that's kind of the setup. Now, how do I specify a given spin chain? How do I specify some physics? It's going to be the notion of interactions. I need to specify how neighboring or like degrees of freedom interact with each other. So there is I is here like it's a compact support. It's going to be typically a one side, 2, 3, or maybe 4 sites, consecutive sites of the chain. For most physical systems, it's barely more than that. And I'm going to pick a self-adjoint matrix acting on these 4 sites. And this is going to specify how these degrees of freedom interact with each other. The Hamiltonian, finally, is just the sum of all these local operators. So these operators here, they are in the local algebra, but then I can embed them in the total one by just tensoring with the identity. And then by summing over all of them, I get the Hamiltonian. So here it's a setup where all degrees of freedom interact with their neighbors in the same way. It's like translation invariant in this. So this Hamiltonian specifies the dynamics. It tells us how the systems evolve in time. So once you're given such a system, the main question we're usually interested in is what is the spectrum of this model? What is the spectrum of the corresponding Hamiltonian? Since it's auto-adjoint, it's going to be some real eigenvalues. And here I order them I use like a specific way for writing them, which I'm going to make clear in a second. And typically, one of the first questions we ask is whether the spectrum is gapped or gapless. So what does that mean for the system to be gapped? So it's a notion that really only makes sense in the infinite volume limit. And this is the statement that you have, you have a set of like the smallest eigenvalues, which all converge to the same value in the infinite volume limit. And then the distance between these eigenvalues and the next one, which corresponds to what we call the first excited state, is larger than a positive constant that is independent of the volume. So you have a spectral gap between a bundle of like some eigenvalues that converge to the same value and then the one of the first excited state. So whenever this happens, we say that the model is gapped, otherwise it's going to be gapped. So why do we care about this distinction between gapped and gapless? It's because when you have a physical system that is gapped, you're going to have like very specific properties that we can exploit. And so for now, I'm going to specialize to gapped systems. And so I can rephrase a little bit the question I asked initially. We ask what are the ground states of a given physical, of a given spin chain. Now I'm going to specialize to what are the ground states of a gapped spin chain. So this is a question that is very difficult in general, unless your model has some very specific properties, like let's say it's integrable, it's some exactly solvable for whatever reasons. If you don't have these, then it's typically very, very difficult. But we have extremely efficient numerical techniques to access the ground states, so the states with minimal energy. And one of them is this Density Matrix Renormalisation Group, which was introduced by White in 92. So this is where the notion of renormalization is hidden, but I'm not going to say anything more than that about this. And what is it, this algorithm? It's a variational algorithm within the subspace of matrix product states. So what does that mean? So essentially, let me sketch the idea. We are looking for like very specific states in this Hilbert space that is exponentially big, right? And we are trying to find a variational algorithm by tuning the variational parameters and hoping to find the state that minimizes the energy, or at least as close as possible. This is obviously extremely difficult, but the states we are interested in, so the low energy states, so the ground states and the first excited states, enjoy very specific properties when you're in a gapped model. And in particular, they are weakly entangled, which means that it's called the correlation length is going to decay exponentially. And so what it means that these states that are very specific, they are only in a very specific corner of this giant exponentially big Hilbert space. And so instead of trying to do some variational optimization within this big Hilbert space, we would like to rather do the variational optimization directly within this corner of the Hilbert space where the physical states, physically interesting states lie. And so the question now is, how do you target this corner of this Hilbert space? And so this is where there is an ansatz that enters. This is the so-called matrix product state ansatz. It's a very specific way of parameterizing states. So the idea is that you pick some, so chi is just some integer, and you can so you can phrase it as picking a chi times chi matrix, vector valued matrix, and you write down the states using these matrices in this way. So the number of variational parameters that you have when you write in such a state is actually just d times chi, which is of course much smaller than the initial size of this exponentially big Hilbert space. Now, of course, if you choose this chi to be arbitrarily big, you will eventually span the whole Hilbert space. But the idea is that by picking a small enough chi, you control the amount of correlation that there can be. And by choosing it small, you can essentially make sure that you will have such a weakly entangled states. And so in practice, you can demonstrate that indeed for a fixed chi that is independent of the volume size, you will approximate well the states that are in this corner. And so essentially what we do at the end of the day is that we do this variational optimization within the subspace spanned by such states for a given chi. So this works extremely well in practice, but we can even do better than that whenever we have a symmetry. So the concept of symmetry is actually central to what I'm going to talk about today, but I'm not going to put as much emphasis on this notion. But so generally speaking, right, symmetry is just going to be some transformations that leave the physical laws of your system invariant. In the context of spin chain, ordinarily, when we say we have a symmetry, what do we mean? We mean that we're going to have a group that is either continuous or finite. And a consequence or consequences of having a symmetry is that you're going to have a collection of unitary operators These operators, they act by conjugation on the operators of your system. So preserving the physical laws means that preserving the Hamiltonian, and therefore means that it commutes with the Hamiltonian. Furthermore, the composition of these operators must preserve the multiplication rule of the group, so they must furnish representation of the group. So that's typically what we mean by a symmetry in this context. The reason why this is useful is because in the presence of a symmetry, then we can distinguish two situations for the ground states. Either the ground states preserve the symmetry. So in addition to being eigenvectors of your Hamiltonian, there will be also eigenstates of the symmetry operators. So in that case, we said that, yeah, so they preserve the symmetry. Or there will be a unitary symmetry operator such that when you act on the ground state, it will give you an orthogonal ground state, so a degenerate orthogonal ground state. Whenever this happens, so we have some states that do not preserve the symmetry, at least one that does not preserve the symmetry. We talk about spontaneous symmetry breaking. It means that there is less symmetry in the ground state sector than you have at the level of the model. And the model always commutes with all the symmetry operators, but in the ground state subspace, we have this breaking of the symmetry. And this concept that is central in physics, of course, allows you to both organize the properties of your physical system, but also to organize physical theories amongst themselves. And in particular, this leads to this so-called kind of Landau paradigm for the classification of gap phases of matter. So here, by phase of matter, I mean some path-connected component of models, so gapped symmetric paths. And the question is to try to classify these path-connected components. And so in the case when you have, we know there is a symmetry G, by just exploring the different possible patterns of spontaneous breaking, we can classify these theories. And so this leads to a classification in terms of so some subgroups of the group, and then some cohomology class for this subgroup. So here the idea is that these subgroups represent the amount of symmetry that is preserved in the ground state subspace. And even given that, then you can have states that transform differently under that symmetry. So even though they are eigenstates, they can still transform differently under that symmetry, and this is classified by this second cohomology class. Okay. So that's the usual story. Something that is interesting, and this is why we are looking at the contribution of symmetries in the study of such thin chains, is that when you run this DMRG algorithm I talked about to try to find the ground states of such spin chains, you realize, and this is something you can make precise, that the ground states of a phase where the symmetry is spontaneously broken are always easier to simulate. So what does that mean? It means that for a given number of variational parameters, for a given amount of resources, you're going to achieve a better accuracy if you're looking for ground states that break the symmetry. So if you're in a phase where the symmetry is broken. The idea is that, loosely speaking, is that if you're looking for states that are symmetric, being symmetric means that they have certain structure in order to be able to preserve the symmetry. Also, as I said, they are the different ways that they can be symmetric is classified by such a second cohomology class. So it means the information of this cohomology class must be in the state. And all this basically takes some sort of variational parameters in order to encode this structure. So you have some redundancy every time you're looking for such states. And this means that for given resources, it's not going to be as efficient to simulate them. So this leads to then kind of the question is that, okay, could we always simulate ground states of a phase that is symmetry broken? Because then it will always be efficient for this reason. And indeed, you have such a statement, which I'm going to spend most of my talk trying to motivate, is that for any model that represents some gap phase, you can always find a dual model that is going to have a dual symmetry. And with respect to that dual symmetry, is going to be in a spontaneously symmetry broken phase. So here, dual in the sense that there is essentially a unitary operator that will relate the spectra of these two of the two Hamiltonians. And So in practice, what do? Is that let's say you're given a model that represents some gap phase, right? You can construct this dual model, and so basically what was done in these papers was essentially to explain how to construct these dual models. You will simulate this dual model, and then you will use this unitary mapping in order to find the states of the original one. There are two caveats to this approach. I would say actually more than caveats, more like two features. The first one is that this dual model may not be a spin system in the sense that I defined at the beginning. In particular, I said that the Hilbert space was a tensor product space for the spin chain. Here, we may end up with a model where this is not the case. So you end up with models that are not built on tensor product spaces, but that's okay. It requires like accommodating the usual DMRG algorithm. And also, dual symmetry of this model may not be maybe non-invertible. So here the idea is that you end up with a model that still has some operators that will commute with the Hamiltonian, but they will not furnish the representation of a group. Rather, they will be compatible with kind of some fusion ring structure. But that's fine. And so bringing everything together, it leads to essentially the optimal way of using this DMRG simulation to find the ground states of some gaps. And so now what I want to do is kind of to explain this bit. How do you relate the gapped phase of a model to a symmetry broken phase of a dual model? And to understand this, I need to kind of take a step back and think about these things much more generally. Okay, so the starting point is the idea. So this is something that is partly proven in some cases, largely believed under some assumptions, but it's kind of still a conjecture, is that gapped phases are described at long distances by topological quantum field theories. So the idea is that once you get rid of all the sort of lattice artifacts and you're only looking at the universal properties of your physical systems, all this can be understood from the point of view of a topological quantum field theory. And this means then that the classification of gap phases is closely related to the classification of topological quantum field theory. So let me briefly review the definition of a TQFT, which here I'm defining in a global way. So I'm defining an n-dimensional TQFT as so what we call a symmetric monoidal functor from some category of cobordisms to the category of vector spaces, or some flavor of the category of cobordism. So you can add here all kinds of adjectives depending on the type of physical theories you're interested in. You could add some spin structure, some framing, some G models and everything, depending on the specific type of gap phases we are ultimately interested in. So what does that mean concretely? It means this is essentially just kind of a path integral. It means that to an n-1 closed, so a closed n-1 dimensional manifold, this theory computes a vector space. Then to a cobordism between two n-1 dimensional cluster faces is going to assign a linear map between the corresponding vector spaces. To a cobordism of this type, which is just, it's an open n-manifold that has a single boundary component, which is sigma, is going to assign a vector in the corresponding vector space. And finally, to a closed n-dimensional manifold, it assigns a number. And all these are topological invariants. These assignments need to satisfy a certain number of properties, which are encoded in the fact that it's said to be a symmetric monoidal functor. And so in particular, the gluing of cobordisms translates into the composition of the corresponding linear maps. And the disjoint union of closed n-1 dimensional surfaces translate into the tensor product of the corresponding vector spaces. Okay, so that's the general definition. Now, let me specialize to the case of interest. So we wanted to, initially, I want to classify what I will call G-symmetric gap phases in 1+1 dimension, right? So I have a symmetry G, and I want to, in the presence of such a symmetry, I want to classify these gap phases. On the TQFT side, it means classifying so unitary TQFTs that are G equivariant. So basically, this notion of G equivariant, this is just the way of translating the fact that we want such a G symmetry. This is essentially saying that since here G is finite, is that you can couple your theory with the gauge field. or another way to put it is that you're looking for a 2D TQFT for which you can couple topological lines that will be labeled by group elements. So this is a well understood scenario, and there is a classification in terms of so-called G-crossed Frobenius star algebras, which I'm not going to define in detail. What is important for us is the fact that there is kind of a recipe in order to construct such 2D TQFTs as a state sum using a state sum construction. So basically, starting from some triangulation of your manifold, and then building the partition function piece by piece by assigning tensors to each triangle and then gluing them together. And the input of such a recipe is going to be a semi-simple G-equivalent algebra. Just to say that at the end of the day, classifying these gap phases boils down to classifying such semi-simple G-equivalent algebras, and this is something that is well understood. And we recover the classification that I mentioned at the beginning in terms of some subgroup and then some cohomology class. So now that once we've established kind of this dictionary between the classification of gap phases and classification of these G-equivalent 2D TQFTs, it invites us to think more generally about sort of where does this kind of data show up more generally when we talk about TQFTs. And in particular, there is another place where the same classification shows up. It's also classify what we call topological boundary conditions of now a higher dimensional TQFT, a 3-dimensional TQFT, which is going to be a pure gauge theory. So there are many names for this TQFT. You can think of it as a finite group version of BF theory in 3D, some untwisted version of digraph return. I mean, there are many names. And so I want to elucidate now this aspect. So in 3D, so now we are like going one level higher. What is the situation about sort of the classification of 3D TQFT in the way I've defined them? So there is a very a very general construction due to Reshetekin and Turev to build 3D TQFTs from so-called modular tensor category. So here I won't define this notion precisely. I will say more about this notion of fusion category in a second. Just to say that the kind of the terminology comes from rational conformal-fit theory. Actually, this was first introduced in that context. There is indeed an interplay between CFT and TQFTs. The idea is if you take you take your rational vertex operator algebra of your rational conformal-fit theory, and you look at the category of modules over it, you find such a modular tensor category. So this is where the terminology comes from. I'm not going to deal with this big family of 3D TQFT. I will be dealing with the smaller one, which is due to Turev and Viro, and then generalized later by Barrett and Westbury. And again, this is it's a TQFT that you can build using a state sum construction. So like I mentioned before in 2D, now we have a 3D manifold that you kind of triangulate it, and then you assign some local weights to like each titular region, and you can build your partition function from this construction. Another way to put it is that there is a lattice. You can define these TQFTs that are of the Turev-Viro type. You can define them on the lattice, which is not true of Reshetekin Turev in general. So what is the input of the kind of this state sum recipe for this special class of TQFTs? Is what we call a spherical fusion category, which I'm going to partially define in a second. But you recover, so this is like it's a subclass of the Reshetekin Turev. So in particular, you can recover the modular tensor category by applying what we call the Drenfeld center construction on this fusion category. So just physically a bit more, what does this modular tensor category encode, or more specifically here, the Drenfeld center is going to encode the line operators of the TQFT, right? So the Wilson line operators, if you want, of the TQFT. So in particular, if you, let's say, you're working on, we're asking for like, what is the vector space assigned to the torus, right? So the dimension of this vector space is going to be equal to the number of sort of indecomposable lines that you have in this center. The idea is that you can consider, let's say, you take the solid torus, which has as a boundary like the torus. The TQFT will assign a vector to this manifold in the vector space associated with the torus, and then you can get the other ones by inserting Wilson lines in your solid torus, and you have as many Wilson lines as objects in this Drinfeld center. Okay, so let me say a bit more about the definitions. Okay, this is a bit of a mouthful, but I wrote down here the precise definition of a fusion category. I will motivate briefly each word, but so this is what we call a rigid abelian semi-simple, basically linear monoidal category that has finitely many simple objects, and the identity in this category is a simple object itself. So essentially, what it is, it's a category, right, for which there is a notion of tensor product. The maps between objects in this category all form vector spaces. That is this Becker enriched part. It is abelian, meaning that you can take direct sum of objects. Semi-simple, so meaning that every object is going to be a direct sum of simple ones, and you have finitely many simple ones. Maybe a useful example, like so that maybe if you don't want to think in terms of fusion category, you can think in terms of this instead. Many fusion categories can be obtained by looking at representations over half algebras. So if you're more familiar with half algebras, you can essentially understand fusion categories from this perspective. There are two examples that are, especially in physics, is extremely relevant, and it's kind of understanding well these two examples. It's enough to understand many features of this fusion category. The first one is what we call the category of G-graded vector spaces. This is essentially the way of thinking of a group as a fusion category. And another one closely related is the fusion category of representations over a group. So here it's finite group, finite dimensional representations. So essentially thinking of like the representations and the fact that you have intertwiners between representation, you can tensor representations. That's basically the structure that they form, that everything forms, is a fusion category. So this is a good enough example to build some intuition as to what a fusion category is. So this will be the input of this state sum construction for 3D TQFTs à la Tour-Viro. If you want to get the invariant that is associated with the Reshetikhin-Turev construction, you have to apply this Drinfeld center construction. This is essentially a categorification of the notion of center over a ring or an algebra. But now, instead of asking for the elements that kind of commute with other elements, there is a typo actually here. The second Z should be on the left. You're asking for elements that kind of commute up to an isomorphism. So you're adding some data. So maybe a bit counterintuitively, the Drinfeld center of a fusion category is typically bigger than the initial fusion category, in contrast to, let's say, the center of an algebra that is smaller. Okay, that's very loosely the definition, just to make the connection. So one example of this construction is, so it's particularly relevant. So in the context of G symmetry, like an ordinary symmetry associated with a group, will be the Drinfeld center of this category here of graded vector spaces. And this is something that has many names. There are many ways of thinking about it. This corresponds to the category of modules of what we call the Drinfeld double of the group. It's also the category of modules over what we call the loop group proid of the delooping of the group in terms of action group proid. There are many ways. You can also think of it as the category of G equivariant bundles, vector bundles on the group. And more interestingly, it is also equivalent to the center of this category of representation over the group, which is not a coincidence. This can be traced back to the fact that as they are built from half algebras that are dual to each other, but this notion here, this possibly surprising fact, will play a key role in the following. So I mentioned before, the reason why I started talking about 3D TQFTs in the first place is because there was this, we found this classification of card phases in 2D in terms of these subgroups and this cohomology class. And then I told you that the same data showed up as labeling boundary conditions of a higher dimensional DQFT. So the notion of boundary conditions, I haven't mentioned it yet, so let me talk about it now. So first of all, not every TQFT admits a topological boundary theory, and in particular, out of all the Reshetikhin-Turev, so out of this big family of 3 TQFTs, the only ones that admit a boundary theory are precisely the ones of the Turev type, so are precisely the ones for which there is a state-sum constructions, the ones that we can define on the lattice. All this is actually closely related because you can build this kind of lattice version of the TQFT from the data of a gap boundary, of a topological boundary. So this is all closely related. And in general, we know what they are classified by. They are labeled by finite symmetrical C module categories. So what does that mean? This is again just kind of a categorification of the usual notion of module over like a ring or an algebra. This is basically a category that is going to be acted upon by a fusion category. And this will label the boundary conditions. So actually, let me skip this for a second. Let me immediately set this example. So then we can ask, okay, so in the case where we have a G symmetry, the relevant fusion category is going to be this fusion category of G-graded vector spaces. So now we can ask, what are the indecomposable module category over it? And these were classified, and we recover again, essentially our classification in terms of a subgroup and a second cohomology class. So this makes the connection. One aspect that is important is, and this is actually another way of characterizing these boundary conditions, is to ask what kind of topological or Wilson lines survive on this boundary. So here the idea is that you have you have your 3D TQFT, right? We have a collection of line operators in this TQFT that are organized in what I call this Drinfeld center of the input, right? And when you have a boundary, then you can ask, okay, what happens to these lines as I bring them to the boundary? And you can ask whether sort of these lines survive, or what we say often in the physics literature, condense, meaning some lines will behave like the trivial line on the boundary. And so now you can ask what are the ones that do not behave like the trivial line, what are the ones that will survive on the boundary. And these are, so we know what they are given the data of this boundary condition. And we can compute in particular the fusion category of these lines that survive on the boundary. And these are given by what we call the Morita dual of C with respect to M. This is something that has a definition. It's basically so it's, well, formally this is the category of module and functors of this module category. This has basically maps between the module category and itself in such a way that it's compatible with the action of the fusion category. So that's lots of information. Let me add one quick layer, and then I will go back to more physical pictures. I just mentioned this notion of Morita equivalence. So what I said that so I have I built my TQFT from some input, right? And then I have this classification of boundary theories. And then for every boundary theory, I know what are the fusion category of lines that live on this boundary. And they all form fusion categories. And I said we usually call these fusion categories as the Morita dual of C with respect to M. So we have a notion of, we have an equivalence class of fusion categories. And we say that two fusion categories are Morita equivalent precisely when one is the dual of the other with respect to a given module category. If you're more familiar with the usual notion of Morita equivalence for like algebras, for instance, there is an alternative definition where you can ask for an invertible bimodule between C and D, and that accomplishes the same thing. Why this notion? So what it means that for every boundary, in a way, the corresponding lines that live on this boundary, they form a structure that are all equivalent to each other. And in particular, we have some invariance of this Morita equivalence. And we have that the center of the corresponding fusion categories are always equivalent. So what it means in particular, it means that you can always reconstruct the whole 3D TQFT from the data of the lines that live on the corresponding, on any possible boundary theory. Another thing which play a role later is the fact that module categories over Morita equivalent fusion categories are in one-to-one correspondence. Okay. Okay, so let's be a bit more concrete, and let's see a bit how this looks like in practice. And so what I want to do now is to, so given the type of algebraic structure I just introduced, I want to see how we explicitly construct kind of states in some vector space that are assigned by the TQFT to some closed two-dimensional surface. So I'm starting, so I'm picking some fusion category. Okay, here, if you want, you can just think of it as VecG. So basically a group, if you want, we can start from the group, or but this is more general construction, but if you want, we can just start from the group. We pick a boundary condition, okay, so via a choice of module category. And I'm looking at a specific topology. So I'm choosing a two-dimensional surface. You can pick a torus if you want. I'm choosing a set decomposition for this torus. We could work with the triangulation, but more generally, it's useful to work with an arbitrary set decomposition. So this is something that looks like what you have over there. You have this two-dimensional surface sigma, and I'm picking a set decomposition for this surface. And then the actual topology, the 3D topology I'm looking at is just this surface cross an interval. So some kind of cylinder-like shape. So something that looks like this, where I have two copies of sigma at the top and the bottom. And I'm inducing a set decomposition for this 3D manifold from the one of the 2D surface. So exactly as drawn here. If you want, I'm considering only one layer. So this set decomposition is in terms of plaquettes meeting at edges, and these edges meeting at vertices. I'm only considering kind of one layer of plaquettes vertically. So you should think of it maybe as a thin slab, if you want, exactly as depicted on this drawing. However, I'm not treating this top and bottom boundary in the same way. The bottom boundary, I'm treating it as a topological boundary. So this is really so these are the ones we classified before in terms of module category. This is really asking about extending the TQFT to this boundary, but this is not a boundary, this is not a gluing boundary to which we will assign a vector space in the way when I define the TQFT. And I said that the TQFT would typically assigns a vector space to a two-dimensional surface. This is when this is a surface that is of the gluing type. This is a surface along which we can glue the manifolds. This topological boundary, this is really, we are extending the theory to a boundary, but we are not assigning a vector space to it. So concretely, what it means is that this configuration here is treated like an open manifold that has a single boundary component, which is given by the sigma at the top. And in particular, when I compute the partition function associated with this topology, I'm getting a vector in the vector space associated with the gluing boundary at the top. Okay, so this is what I call this is my vector that lives in the vector space assigned by the TQFT to sigma. And importantly, the actual choice of set decomposition I make do not matter. This is why this is a topological theory, is that I can always change the set decomposition. It will always yield isomorphic vector spaces. And so it doesn't actually matter which set decomposition I choose. The feature that is important for the following is that I can think of this vector space. So this is really the topological invariant that the TQFT computes. I can think of it as the subspace of what I would call a microscopic Hilbert space. And this is a construction that only really makes sense on the lattice. And so how is it defined, this microscopic Hilbert space? So here, maybe I should have mentioned this before. The way I'm assigning degrees of freedom on this is that, so at the bottom, I have the topological boundary, which is labeled by these module categories. So the plaquettes are labeled by object in these module categories. And in the interior of the manifold, the plaquettes are labeled by objects in the input fusion category. every time at every line where they meet, I have essentially a fusion space, if you're in the intertwiner space of the corresponding. So if you think of like in terms of, let's say, represent, so if we take C to be a vec-G, a group, then all these vector spaces are all one-dimensional. If you take C to be the representations of a group, at every line you have an intertwiner space. So you take tensor product of, let's say, 2 or more representations, and you can have a multi-dimensional space of intertwiners between different representations. These are the vector space that lives on every line. And so this kinematical Hilbert space I defined is precisely defined in terms of those. So we are looking at all possible configurations of labels for all these plaquettes. And then we are taking the tensor product of the local vector spaces assigned with every edge. So all these intertwiner spaces assigned with every edge. Right? And from this, you can then recover the actual invariant by building essentially a projector. So the idea here is that if we take now this, so it's the same topology, but now I'm treating both the top and the bottom as gluing boundary, then the TQFT will assign a linear map to it. This linear map is actually a projector. And if you look at the image of this projector on this kinematical space or macroscopic Hilbert space, you recover the one computed by the theory. So that's this. So again, now when I compute this number, which is this vector in my vector space, this gives me one vector in the vector space associated with sigma. This may be a multidimensional, depending on the topology, it can be a multidimensional vector space. How do you get the other ground states? Precisely by inserting, as I mentioned before, like these topological lines, these Wilson lines. And specific here, by inserting lines that are the ones that survive on this boundary. So for every object in this moited dual of C with respect to M, you can sort of insert a corresponding line. And if these lines run along non-contractible cycles of your manifold, these are going to generate different ground states in your different basis vectors in your Hilbert space. Okay, so let's, I'm not gonna actually tell you in detail how you compute the vector, but the idea, which is, so this is based on the way Thioret and Virolisier do it. So there is this notion, as I said, it's a state sum construction. So it's basically you can compute the partition function piece by piece and then putting them together. And the way we do it here is that with piece by piece means we do kind of vertex per vertex. And so for every vertex, essentially what you do is that you insert a ball, and the neighboring plaquettes, they will induce like a graph on this ball that is going to be colored by the various objects that labels everything. Once you project onto the plane, you have a string diagram, something that represents some, well, here it represents a number in the corresponding category, and you can compute like locally all these contributions and ultimately get the vector associated with your topology. And the outcome, of course, of this computation will depend on the input. So it will depend on the choice of C that you made, the choice of M that you made. Similarly, we can compute this in the presence of lines. So here, this red thing is, so this is an object in this C star M, which, if you remember, I defined as saying this was basically a map from M to itself in such a way that it commutes with the action of C. And actually, graphically here, you have kind of this idea that you can think of this line as being kind of acting from M1, and M3 is kind of the outcome of acting on M1, M2 is the outcome of acting on M4, and in such a way that it has to kind of commute with the action of the black line that is vertical, that is labeled by an object in C. So the outcome of this evaluation will depend on the data of this C star of M, like the corresponding object in C star of M. Right. So why did we go through all this trouble? Right? So what we have right now is a way of computing some vectors, right? We have a construction for computing vectors possibly in the presence of lines that are topological. Having topological lines is another way of defining the fact that we have a symmetry associated with the corresponding category that encodes these lines. So if you, again, if you take, let's say, everything to be a G, like everything to be the group, essentially, so C to be this vec G, which is just the fusion category way of saying you have a group. You can always choose the boundary theory to be labeled by C itself. It's like a regular representation. So then everything is kind of vec G. Then what it means you have a way of constructing vectors in the presence of lines labeled by vec G, which is just the indication that you have well, ultimately the indication that we can have a symmetry, a G symmetry. So more specifically, what do I mean? I mean that if I take, so these funny objects, I'm taking my vector, and then I'm taking the overlap, the inner product, with an arbitrary vector that is going to be in my microscopic Hilbert space. So just to recap, this is really the vector space assigned by the TQFT, but I said it was like a subspace of a microscopic Hilbert space. And so if I take any state that lives in this space, I can take the inner product with one of my topological states. Now, since psi does not live really in the vector space assigned by the TQFT, this thing will not typically be a topological invariant. But it's okay. What is important is the fact that this object, the way I can interpret it, is the fact that if I remember the topology of the problem, I have this, so it's a 3D configuration, but it's really kind of a slab configuration. And in particular, since here everything is topological, I can make, if you want, the thickness of this slab as thin as possible. So when I stack a vector on top of this, I can interpret the whole thing as the partition function of a quasi 2D theory, because I can make this here infinitesimally small. And so because of this topology, this essentially behaves like the partition function of a 2D theory. But it's a 2D theory for which we can couple lines that are encoded in this fusion category of lines that survive on the boundary. And therefore, it's going to be the partition function of a theory that is symmetric, that is C star of M symmetric. So this is a very systematic way of constructing 2D partition functions that are symmetric. Now, so just to emphasize, this topological part essentially encodes every theory, let's say in 2D, has a sort of topological and local contributions, or topological and geometrical contributions. The topological vector on the left takes care of all the topological part, while psi will encode kind of the local properties of these theories. So the thing on the left will take care of all the kind of the symmetry and will encode all the symmetry properties associated with the fact that you have a symmetry, while psi will encode all the kind of the local dynamics of your theory. The thing, so now we may ask, why did we, so this gives you a way of building symmetric theories in 2D, starting from a higher dimensional theory. The reason why we did it like this is for the following reasons. Is that if you keep everything the same, so the recipe is exactly the same, you choose psi in the same way, I mean, you do everything the same, but you just change the boundary condition that you chose, the topological boundary condition that we chose at the bottom. If you just change that, you're going to end up with the partition function of two theories that are dual to each other. I can't really demonstrate it, but these are actually theories that will be related by the gauging of a finite symmetry. And in that case, you can show that this induces a duality. And so this is why we kind of constructing things in this way, so that we have access to, we can do this kind of tuning and just change this parameter, which is the boundary theory, and easily go from dual theories to one another. Now to go back to the initial question, which was to understand, so we want to understand gap phases. In particular, we want to understand, so 1 + 1D gap phases that are symmetric, and therefore understanding 2D TQFTs for which we can couple with some topological lines. So now we can ask, how do I, what do I need to do in order to make sure that the theory I end up with here, the 2D theory, is itself topological? And so from the construction, you can maybe intuit the fact that essentially then you just need to choose everything to be topological. And so in particular, you need to choose the state psi at the top to be itself topological, and therefore to be itself labeled by the data of a topological boundary condition for the 3D TQFT. And indeed, this is, so you can, from this picture, you can, so this can be made more precise, but it leads to the statement that, so C-symmetric unitary 2D TQFT, so 2D TQFTs for which you can couple topological lines labeled by a fusion category, are going to be classified by the module categories over C. Right? And so in particular, we recover the VecG, so in the case of G-symmetric TQFT, we recover the classification we talked about before. Now, I will skip these details, but you can, this is just now the question is, how do you actually construct the psi, this vector psi from the data of the module category? You don't actually construct it directly from the module category. There is an equivalent description in terms of some algebra, which you can promote to Frobenius algebra. And then this is really from this Frobenius algebra that you build the psi. Okay, but so what is the conclusion of all this? So let's say I want to describe a gap phase that has any really symmetry and going in fusion category, but let's say let's C to be G, so just like a G symmetric gap phase. I know that these are labeled by boundary conditions for the corresponding 3D TQFT built from VecG. And so in particular, I can realize the theory, the corresponding TQFT associated with this gap phase in the following way, where I'm picking, so the starting point is C or VecG in the case of G symmetry. I can choose the boundary condition at the bottom to be C itself. So then I'm going to have the lines are going to be labeled by C or VecG in the case of a G symmetry. And then the thing that I put at the top will control what gap phase I'm talking about. Okay, and the data of this gap phase is again itself a module category that is that I can also express in terms of an algebra. So this 2D TQFT correspond to the C-symmetric gap phase that is labeled by the module category at the top. And this, what it means that basically this is a gap phase that preserves the symmetry encoded into the algebra A. In the case of VecG, here A is just a subgroup with potentially some 2 cocycle. So this will be the gap phase that preserves the symmetry A in a specific. You know, the question we can ask is, so what happens if I keep everything the same, but just change the boundary condition at the bottom? So if I change the boundary condition at the bottom, I'm changing the kind of topological lines that survive at the bottom. So I'm ending up with a 2D TQFT that is now coupled with different topological lines encoded in a different fusion category. And therefore, the interpretation of this as a gap phase is not immediately clear, because the classification is supposed to be in terms of module category over the symmetry, but now I changed the symmetry, so the data at the top, it's not immediately clear what kind of gap phase it labels. This is where this results I mentioned before kicks in, the fact that so Morita equivalent fusion categories admit the corresponding module categories are in 1-to-1 correspondence. This is some kind of 1-to-1 correspondence. And so in particular, this allows me to state the following, that when I change this topological boundary theory at the bottom, the 2D TQFT I end up with corresponds to a C star M symmetric gap phase that is labeled by the module category. And this is something that I can compute. It looks like the definition a bit of C star of M. This is going to be, again, some maps between the corresponding boundary theory or the data labeling this boundary theory, such that it commutes with the action of C. Okay, so this tells you how to, so what this tells us, it tells us how it tells us how, when we do these dualities associated with changing these boundary conditions, it tells us which gap phase we end up in. It gives us the mapping of these gap phases under these corresponding dualities. And now I can ask the question I asked at the beginning. I asked, I wanted a dual theory where the symmetry was broken. So the symmetry is broken when, in these pictures, when the boundary at the top, the module category at the top, is the same thing as what encodes the lines at the bottom. And so the reason why is because you have, so let's say if you have a G symmetry, when you're breaking, you're breaking completely the symmetry, you have as many ground states as you have group elements in your group. So you have as many ground states as you have line operators. And here, the objects in these module categories, they precisely label the ground states. So you want to have this module category to be the symmetry category itself. And this is when you have a symmetry breaking. And so here, this tells us exactly which duality to do. We have to do the duality that amounts at picking M to be whatever is the data associated with the one at the top. So physically, more concretely, if I go back to the usual G symmetric case, the statement is actually quite simple in that case. It's just saying that gap phases in general are labeled by a subgroup and a cohomology class. This tells us that the subgroup A tells us that you have that amount of symmetry that is preserved in the gap phase, and the ground states, they transform in a way that is classified by this psi, which is this cohomology class. From this, to get to a gap phase where the symmetry will be completely broken, you just need to do what we call the twisted gauging by psi of the symmetry A, that is precisely the one that is preserved in the phase. Okay, so that's kind of all I would say somewhat formal, but but we can go further than this. Is that all these kind of sort of abstract algebraic manipulations, we can turn them into actual operators, and in particular, this duality operator that is supposed to relate the spectra. So going back to like the Hamiltonian picture, that is supposed to relate the spectra of the dual models. From this knowledge now, like from we know that what is the algebraic structure that will encode the duality, we can actually build the corresponding duality operator, which then allow us to accomplish what we wanted in the context of these DMRG simulations. So let me just leave you with the kind of the motto of this result is the fact that so under some certain assumptions, every symmetric gap phase can always be studied actually from the point of view of a symmetric gap phase where the symmetry is completely broken, which aside from being useful for the type of numerical simulations that I mentioned, is kind of conceptually useful because these phases that break the symmetry, they are sort of the simplest in many ways. The ground states are typically the ones that have the least amount of entanglement and so on. And so all the properties of the other gap phases, we can always understand them from the viewpoint of this simple phase. And all the features that differ from those of this simple phase, they just stem from the corresponding duality relating the corresponding gap phases. And I will stop here.
We have time for some question.
Please go.
Junction.
I mean, if I think about how to classify all the gap phases in 2D, I would start from all the vertex operator bars, classifying all the Vollindo lines, do all the obifolding, and then twisted gauging, and then deform my CFT and the flow to IR to think about which sure, gap phase is this completely equivalent to what you?
So you're not starting from gap phase in the first, but you're starting from anything, and then you see where you flow, and then you want to see.
I always start from VOA, and then I find a minimum representation for this VOA.
But I mean, here we really start directly from the. We don't really flow to a gap phase. We just kind of start from like, okay, we know what are the properties we expect in a gap phase. So the original classification of these things, they were really at the level of states, right? People ask, okay, classified states, what are all the possible ways for states to be symmetric? And find already this classification in terms of subgroups, and so it's directly in the kind of,
there's no flow.
there is no flow. Yeah, you're just directly asking. Let's say we flew to a gap phase. What can we find, right? But this is not saying that you cannot recover it from the point of view you mentioned. Because would you expect something else in that case?
I'm just wondering whether they are equivalent. So.
I mean, it should be.
So just a very naive question. So if you have a symmetric gap phase, I suppose, but I'm not sure, that it's somehow the presence of the symmetry is something that you can see from the spectrum, right? And then you have this map that is very complicated, that map the symmetric system to a system where there's another system where the symmetry is potentially broken. And I just wonder how these special, say, states that are predicted by the symmetry, so in some sense are protected, how they are mapped into.
Yeah. So that's kind of that's exactly the whole point. Right? So when we do these numerical simulations, especially if you're simulating like a symmetry protected phase, you're gonna have some degeneracy, as you said. This is the signature of having the symmetry. You get some degeneracy in your spectrum, and effectively, what you want to do is that you want to trade this degeneracy for degeneracy in the ground state sector. So instead of trading degeneracy, instead of having degeneracy in the spectrum of a single state, which degeneracy translates into less optimal simulation, by going to symmetry broken phase, now you have multiple ground states, so this degeneracy translated in this way. And by simulating then a single ground state of the symmetry broken phase, you can look at the spectrum, the degeneracy is lifted. So you have a spectrum that drops like much more rapidly, and this translates into much more efficient numerical simulations. So that's exactly the idea.
Another question?
Yeah. That question. Usually when you have broken symmetry, it's on a line of a first order phase transition, right? So if you think about the ferromagnetic phase, you can.
Sure. Yeah.
And am I right in saying that usually DMRG is tricky when you have first order phase transition?
You mean at the first order transition?
Yeah, you are at the first order phase transition if you simulate this simultaneously broken symmetry, right?
Not necessarily. No, I mean like where
at least in the usual examples, you have a Z. If you have
like easy
Z2, if you break Z2, then you have Ising one first order transition. You are sitting on the first order line, right?
No, you are.
I mean,
you're at the gapped phase, either up or down.
I mean, yeah. I mean, here I'm definitely only talking about the gap phases, right? So
yeah, but the gapped phase is where the first order line is, right?
Right.
So isn't numerical simulation tricky there? You have two optimal states.
Well, so the thing is that, so we're working on finite size, right? So typically we will always prefer an even ground state. So we're working with the way it works in practice, more in the level of implementation. We're working with like open boundary conditions, finite size. So you don't have genuine symmetry breaking because you're only at finite size. We will, furthermore, we can target a specific ground state by specifying the boundary conditions. And so it's especially relevant in the case of breaking of non-invertible symmetry, which will happen as soon as you have if you apply your recipe whenever you have a non-abelian group, because not all ground states are actually equivalent. So some of them have less entanglement than others. And so we will look at the one that have less entanglement by specifying the open boundary conditions.
So maybe we can continue a little bit more on during the break, and let's thank the speaker again.